All right. Hello, everybody. Good morning. So, before starting the course, do you have any question about last week or last lessons? Okay. So today uh, we have kind of important topic. So far, we talked about the model evaluation, the accuracy of model, and the linear, nonlinear, multivariate regression models. But the missing part of the point is that how we can train the model, how we can, after we have the data set and after we have the initial random model, how we can train our intercept and slope in order to cover our data to do the prediction. So today we are going to talk about that. Again, I'm drawing quickly the uh, data points over here. So always when I was talking, we initialized and we said that we have the model that we defined it as x and y, and we consider that this model already fit. But now today we want to see, okay, by knowing that the intercept will set where the line is and the slope will set the slope of the line, the model that we have, how we can set this. This is very important to understand. And after today's course, after you understand the how to do that, this is going to work with not only regression models, but also more advanced models. We will use it in neural network, we will use it in deep learning models, and the very advanced reinforcement learnings that are using deep learning models. Deep neural network also using the same concept mostly in order to train the model. So today we are going to talk about gradient descent, stochastical gradient descent, and later on we will move toward cross-validation and see if after we having that, how we can evaluate how our model is good enough. So as I mentioned, we will start with gradient descent, then we talk about the stochastic gradient descent, then we talk about SGD with mini batch. We will see there are some problems with gradient descent. We will improve it with stochastical gradient descent. Then we will see that it has some problems. We will try to increase it with adding mini batches. So if you ever heard about or worked about neural network or deep learning, you will definitely know what is it. But today we will going to from scratch see what is it and how it is. Then we talk about cross-validation approaches. A couple of famous cross-validation approaches are named k-fold cross-validation, stratified k-fold cross-validation, leave one out cross-validation, LOOCV, and the time series cross-validation for time series data. And then later on, we will talk about group k-fold cross-validation. And after today's course, you're supposed to have a deep understanding of how the process of training our model is going to work. How, when we are talking about machine learning, and when we are talking about finding the weights, proper adjustment weights for our model, what do we mean? Today, all of those will be obvious for you. Okay. So let's start with gradient descent. It's very popular, very important algorithm in machine learning. It's critical to know how it is. It is simple, but let's break it down from beginning. We say it is an optimization algorithm to find minimum of the cost function. So we have optimization algorithm that we want to minimize the error of the prediction. So at the beginning, we have a, like, if we are talking about simplest model, linear regression. So we have a line, we have a model, that this model do some prediction, but it has lots of errors. So we want to minimize it in order to achieve that one. So that's called optimization, and we can have maximization problem or minimization problem. In this case, we want to minimize the error of model that we have called gradient descent. So in order to do this, what we should do? We compute the partial derivatives of the cost function. So if we become able to calculate the partial derivatives of cost function, of course, we have many parameters. Regarding each one of the parameters, we can kind of find a way to improve our model. But in order to understand this, we will break it down more. First of all, we say, okay, what is the gradient descent applications before that? Before getting into the details, you can use it in linear regression. You can use it in logistic regression. We will study it. It's very popular and powerful algorithm for classification tasks that from next week we are going to study to talk about those. They are applicable in neural network, as I mentioned. They are applicable gradient descent, statistical gradient descent, and its family is applicable in support vector machine. We will see what is it and how it is working. It is applicable in principal component analysis, PCA, very popular algorithm in machine learning. In clustering, unsupervised learning, it is applicable. Recommendation systems, it is applicable, usable, and etc. Of course, as I mentioned, with advanced deep learning models, also it is pretty common to be used. So to understand what does it mean when we are talking about the partial derivatives and train our model by calculating partial derivatives of these, maybe you feel, oh, okay, it should be something complicated. It is not. Let's see how it is. So everybody, please pay good attention. This is very important. If you learn this, is kind of you learn the core of the machine learning, how to train the model, because it is whatever we're doing. Actually, a part of that is like training part, and this is gonna work there. So what is the partial derivative? We say we have a function that is constantly changing through the time. Change in input, change the output, and we can use partial derivatives to understand the amount of change. What does it mean? This is the input, right? The change of the input changes the output, right? If I change the x, increase the x, output is changing. This either in this model or that new one. Let me simplify this. Maybe this blue one. If I change, there is change. Now, that change, I should kind of be able to capture it, right, in order to understand it. If I want to understand it, I can take the partial derivatives that we can formally say the partial derivative is a derivative that shows the change only in one of the chosen variables. Here we have only one. If you have multiple variables, for each one, we can take the partial derivative and understand how much is the change. So based on that, as I explained, we can understand how function changes with respect to each variable while keeping the others constant. So basically, the idea is if you have multiple variables, we keep all of them constant and we change one. And based on changing one, we will study how the change affects the output. So in multivariable functions such as simple function fxy, for each independent variable, we calculate the slope separately. So when we are actually calculating partial derivatives, we are calculating the slopes to capture the behavior of the system that we have. Look at this plot over here. If you have a look, you can see that we have a model, that this model, in this point, in this black small point, we can calculate the slope. So how much is the slope of this point over here? Why we are calculating this? Because we want to see how much the change, if you calculate 2 points in the x, like increase the x and change it, we will see how much the slope is changing. And we can study our prediction model. to minimize the objective. So let's see a very simple example of mass. I consider you are not familiar with partial derivative. Let's have a look. If you have a function simply like this, f of the x and y is equal to x to the power of 2 times y to the power of 4. So we have this. If we take the partial derivative of this, what happens? We can write derivative of the f, x to the power of 2, y to the power of 4, and we do that with respect to the x one time, and we can do that with respect to the y one time. So if you take the partial derivatives based on the x, you will have 2x y to the power 4, because this power 2 will be comes to times and will be deduct by 1. So that's how we did it in simple math. I'm pretty sure you're all familiar with it. So it means that this is a model, right? This is a model like that. If we calculate this now, sorry, if we calculate this now, what we will have? We will have the slope. The slope of where? The slope of that input x in x direction. So we can do the same thing, calculating the partial derivative based on the with respect to y. If we do that, then the output, the result will be like this. The y, the power to the power of 2 will be subtracted by -1. Then 4 times of the x to the power of 2, y to the power of 3. So if we do this, what's happening? We're calculating the slope. Clear? Any question? Simple math so far. So we say, okay, if we assemble slopes of all variables into vector, we call it as gradient. So when you have a function, you can calculate partial derivatives with respect to each variable, right? One time x, one time y. If we collect them as a vector together, we call it as gradient. Clear? Now, pack of those is gradient. Now we say, if we assemble all the partial derivatives of the all variables, then we call it Jacobian matrix. So if I do partial derivatives of this function for both of them and pack it as one, we call it gradient. And if we do it for all the possibilities, then we can call it as Jacobian matrix. So far, this is math. Jacobian matrix, we are not going to use it now. We use it in some other cases. But for now, when we are talking about gradient, you should quickly think that, okay, we have a function. That function, I calculated the slopes for each one of them, the derivatives of each one of them, each one of the variables, and I pack it as one pack. Now, okay, now let's say we know exactly what it is. How we can apply the gradient descent? The question comes, how we can bring it into the machine learning and linear model, linear regression, and how we can use it to train our model. We say in linear regression, we needed to estimate in the coefficients of the theta hat 0 and theta hat 1 for the model, right? What was our model? We said that in linear regression, in simplest form, our model is y hat. Predicted model is equal to theta hat 0, intercept, and theta hat 1 times x1. Intercept was indicating where it is lying, the location, and the slope was saying how is the location of the model that I want. So we want to find values for this, right? I want to put like a number here, 1, 2, then change it until minimize the error of my model. So in order to do this, we have a couple of steps. What we do, first of all, initialize the parameter. So this is the linear regression simplest model that I can have. This gives me that line. Then the first step, what I do, I initialize the parameters randomly in gradient descent algorithm implementations using what we are talking now. So you set some random numbers over here. We will see it in a couple of minutes in code implementation too. So choose initial values for theta hat 0 and theta hat 1 randomly, whatever it is. For example, you can initialize them as 0, 0, 2. So you start a model with 0, 0, for example. And if you do that, I also show visual example. So in this plot that I created for you with the code that we have. So this is the data set that we have for advertising and social media. And this is amount of sale, right? Now, we want to train our regression model to predict this data with gradient descent. So at first step, we said that we want to find this prediction through this line, right? I initialize them as 0, 0. If you do that, 0, 0, then you will have this line, right? Why? Because if you put 0 here, y hat is equal to x1. So x1, whatever is increasing, y hat is equal to x1. You will have a line like this as prediction model at initial state. So after first step, we move toward step 2. In step 2, we calculate now the cost function. We want to see, okay, we did that, 0, 0. How good is that? Maybe it is very good. Maybe it is not. We want to calculate it. That cost function will tell that to us. For calculating cost function, we have multiple options. We studied many of them, but common one, popular one to be used is, for example, residual sum of square or mean square error. Depending on the algorithm implementation, we will see there are different cost functions. We will study many of those later on, depending on algorithm. So let's say here we are calculating mean square error, the simplest to understand. So we need to calculate the error, mean square error between the prediction and real data. Prediction is this line that I have, real data are those. So how was it? Mean square error was average of the differences between prediction and labels or real data. If I want to write it formally, as I mentioned to you already in machine learning algorithms, in most of the case when you say J is cost function, or sometimes shown by E2, error of the model. J of the theta hat 0, theta hat 1. When you see this, it means that I want to calculate the cost function, the error of the prediction of these two values that I found. So I can write J of the theta hat 0, theta hat 1 is equal to simply the mean square error, also called as loss. So when you see this, sometimes also has been shown with L, big L, or Laplace. It's shown by Laplace too. So loss or cost function. Any question? Everything clear so far? All right. So step 1, we had the model. Step 1, we initialized with random numbers or 0, the thetas. Step 2, we implemented mean square error to calculate the error of that model. So if we calculate this one, we will have something like this. I also write some code that shows visually what's happening. So if you calculate mean square error per each one of the data for the prediction, what my model says, what is the error per each one of the data? Like for number 1, my model says 0, but really the label is like around 12. For 300, this data like says again 0, but is like 22, something like that. For all of these, I do the same. And if you do the same, I also calculate it and show for you. Mean square error of this model is 445.93. That's the error that I have for this prediction model. Okay. After second step, that we evaluated the model, by mean square error, we say, okay, let's move to third step. But before that, I want to have a note for you here. So when we are saying that j of the theta hat 0 and theta hat 1 is equal to the mean square error, MSE, the average of the yi subtracted by y hat I, the point is that, so sometimes I see some students misunderstand or do mistake understanding this. So y hat of the I, what is the y hat of the I? Y hat of the I is my model, right? And this my model is written like this. Y hat of the y hat is equal to theta hat 0 added by theta hat 1 x1. This can be any model. This can be very complex deep learning model, neural network model, anything. For now, we're talking about simple linear regression to understand. So my model, prediction model is this. And if I replace it, my loss function looks like this. So make sure that you get the point. So loss of the theta hat 0, theta hat 1 will be like y minus this, my model. What is prediction? So it means that I want to give the x, like the value 10, then times this value plus this value will give something. Then I subtract it and I can calculate the error that I have. Clear? All right. Now we can calculate the gradient. So gradient, what was the gradient? The gradient was two partial derivatives. Remember? 2 slides ago. I said that partial derivatives depending on variable A, variable B. So now we want to calculate it. What we do, we calculate the partial derivatives of the cost function regarding theta hat 0 and theta hat 1. We have two variables here, theta hat 0 and theta hat 1, that we want to find it. So what we should do, we write the gradient of the loss function according to theta hat. So I want to find the slope of change actually. Simply, if I want to explain simply as gradient again. So of course I will have two times of calculations. One time depending on theta hat 0. I also pointed some notes here for you that partial derivatives of cost function with respect to theta hat 0, or when it changed the or when it changed. So it means that when theta hat 0 changed and other variables like theta hat 1 kept constant, we are calculating the partial derivatives. Another point is that the sign here is important because shows the direction of the slope for me. So what I do, I get partial derivatives of the cost function, that function, with respect to theta hat 0. If you do that, if you get partial derivatives of this, you will have something similar to this. Why something similar, not exact? Because if you calculate that, it will be 1 minus 2 over n of these. But for simplicity, it's common to write 1 over n of this. So after getting partial derivatives of that term over here regarding theta hat 0, we will have minus 2 over n, and this equation, for simplicity, we write this. Why for simplicity? In next slide, you will see. We have a learning rate. That learning rate can find us for that negative value, minus 2 value, with the weight that we have. So it's not necessary to put it here. You can keep it, but it's not necessary to keep it here. Then we do the same thing for calculating gradient depending on theta hat 1 of cost function. And if you do that, simple math, you will have this one, this term. The difference is that here we have xi1 times xi1 from there. Now, I also visualize for you for make it understandable, much more understandable. So, for the mean square error, the model that I had, after calculating the mean square error, Now we calculating partial derivatives, theta hat 0 and theta hat 1. And I printed the values that we can find out after calculating this. Partial derivatives of theta 0, partial derivatives of theta 1 over there. So actually what we've done, we calculated the rate of the change based on theta hat 0 and theta hat 1. Question, why do you think that we are trying to calculate the amount of change? Can you guess it before I explain to you? If you can guess it, it shows that you 100% understand what is happening. If you look at that, so what we are doing, this shows me a prediction line. We are trying to find, our machine learning model tries to find values for this, right? And we said that initially we start with 0, we put 0, 0. Now, our machine learning should change them to some proper value, right? Should find good values for this, like maybe 2.5 here, 3 here. But how it can change it? Machine learning, how, or linear regression model, how can understand what to change and how to change? We calculate the slopes of error. We calculate gradients, slopes of error, so that machine learning have idea of how to change, which direction to change, first of all. Second, how fast to change the values in order to minimize the error. How that can happen? That can happen in next slide. Just one note before getting to that part. We say that this part, if you use another metric instead of mean square error, then your partial derivatives will be based on that one, that new calculations, and your output, of course, will be different. The equation will be different. Depends on which kind of metric you're using. Then we come to update the parameters. Update the parameters is the idea that I explained to you. We want to update the values of these in order to achieve what is the best. I don't know, I just read something randomly there. So we update the values of theta hat 1 and theta hat 0 using gradient and learning rate alpha. This learning rate alpha is very important also in almost all of the algorithms we have it. All machine learning algorithms almost that they are learning, there is learning rate to how fast my algorithm should learn. We will discuss it more in details. Now how we can write it? We calculated two slopes, right? Two gradients, one for theta hat 0, one for theta hat 1. Now we can use it. We can say theta hat 0, the new value, is equal to theta hat 0, previous value, whatever it was inside, subtracted by learning rate alpha times the gradient that I want to calculate, and I calculated in the previous slide. So the gradient calculation based on theta hat 0 will be staying here, times learning rate, how fast I want to update, subtracted by that term, subtracted by the theta hat 0. Actually, theta hat 0 subtracted by that term. The same process for theta hat 1. I calculate the gradient times the learning rate, how fast I want to update it, how fast I want to change toward that direction. So this gives me the change direction, and this gives me the how fast I want to change in that direction, and then update my theta hat 1. So by applying these two steps in each iteration, actually we are updating our values in order to, for example, if my model was here, so my gradient, my error, my calculation says that, okay, the direction is this side, and how much it also shows the magnitude and how much it is the slope. Then based on that, I times it with learning rate and try to adjust it, increase the values, for example. So 0, 0 becomes this one. Then the next step becomes 2.6, for example, and 3.5. So we continue this until converge. And what does the convergence mean? Means that mean square error is minimized. We cannot improve it more. So let's continue by slide to see what's happening. I'm showing visually again what is happening there. So we had this one. If you remember, we said that theta at 0 and theta at 1, intercept and slope are 0, 0 as initial. Then I apply this learning rate for alpha, usually very small value. We will discuss this more also, but usually very small value. Then after calculating the first stage of partial derivatives of 0 and 1, I calculate the new one by updating the theta hat 0 and theta hat 1. So one stage of doing that and doing this, you will achieve this value. Then mean square error, that was 445, now reduced to 105. So after calculating the gradients of this and updating by learning rate, your model from here will move there. Means that these values, if you replace it with theta hat 1, theta hat 0, you will achieve something like that by calculating the graph. Step 5, repeat it. Now run step 2 to 4 until the cost function gets minimum or some stopping criteria that usually is 2. The change is too small. The theta hat 1, theta hat 0, changing very small, then you say, okay, this is ignorable, like change too small. Or you set some intervals. You say like 500 iterations, 1,000 iteration, or 100 iteration. How many times I need to try? Then when that ends, then your algorithm stops training, stops finding, adjusting the model based on that data that you pass. So I visualize the implementation code. I will pass the code implementation to you today. You will have some practice. That was the first iteration, 0, 0. This is second iteration, as I showed you in the slides. If you continue more iterations, I apply the third iteration. So this is the third iteration. You see that mean square error is 105 here, 105. Here, 102, decreased. And if you continue more iterations, in this stage, you can see that mean square error get to 78.68. From there, like 70. This is like I'm showing red one is old one, green one is new one. Is almost the same. This is 78.68. This is 78.67. A little bit less. But if you look at the model, is predicting very well, right? If you want to, if I ask you to draw a prediction line for this data, you would definitely draw something similar to minimize the error. And this is how it works. Gradient descent, how work on our model with 5 steps that we calculate. So, any question? Is everything clear? Now, everything that we studied up to this week, you just apply gradient descent, you train it. But we will see. For example, here, we calculated only for linear model. If it's nonlinear, how we do in next slides is going to come. So, the first question that we need to answer, the learning rate challenge. You might say there was an alpha learning rate. How should I know what should be the learning rate? So there is a challenge with that. That first, usually we call it as hyperparameter, and you as developer, you should find that learning rate. You change it to see which learning rate is best. There are some predefined range usually that we go into that range, but you should change it with your code usually that you can detect it. There are some automatic ways, some algorithms that can help you to find the learning rate, but it's still very pretty common to use it manually. So the question is, you have this cost function. This is cost function. Don't mix it with the prediction model. This is cost function. Shows the error, right? So the learning rate, if it's small, every time your model cost, error of your model, so is decreasing, right? Each one of these is decreasing the model cost. It means that you have a model, you update the parameters theta at 0, theta at 1, then cost function at the beginning is here, then later decrease, later decrease. If it's too small, then your model convergence, its number of iterations that your algorithm should run with gradient descent is too long. You know, many steps, small changes until it converges. This is the minimum possible error that we achieve. This is called small learning rate problem. On the other hand, if the learning rate value is too big, if you adjust it for big value, what happens? Then it's like a step size. So step size are too small here, step size is big here. What does it mean? It means that from here, if your learning rate is too big, your algorithm in towards that direction of the minimization suddenly jumps too far. It's like going down very far, right? If it goes here, so it actually passed the minimum. And from here, the slope of the cost says that going down is here. Again comes back. The step size is too big. And from here, mighty again goes there. And never can find the minimum because the step size is too big to go down. And that's big step size problem. It's like you can imagine there is a hole and you want to have a big step size. Impossible you can go inside. Every time you go, as you jumping on that. It's the same problem. So update of is like these parameters quickly change. Like instead of coming to 0 to 2.5, you suddenly change it to 10 or suddenly change it to 100. So the step size, the amount of change is too big. You quickly change this. If you quickly change this, the line should suddenly change too big. So never you can find the proper values. How you do that? You try different learning rates to see the plot, the results, the output to see what's the proper value for learning. So if you have a stable learning rate, you can avoid local minimum and convergence smoothing. And local minimum means that if your cost function is like this, because cost function is not always like that, can be like this, then your algorithm may be stuck here. So you want to minimize, gradient descent comes, minimize, stuck here. But if you have bigger step size, proper step size, maybe your algorithm can run away from here and come find this minimum. That is much more smaller value than that cost function over there. Okay. If we continue learning range challenge for our example, if we set quick learning rate, what happens? The implementation, the code that I'm going to give into you, first of all, is the same thing that I'm showing as data here, right? So I've written the code for implementation here. Then the thing is that if we set the big learning rate and the small learning rate, I wanted to show you what's happening. For example, if you try a bad learning rate that you can do it yourself with the code to see, for example, if you set the learning rate as 0.0001, that is considered as big learning rate. What is going to happen? So initialization was this. We said that we We assume we initialize our theta at 0, theta at 1 and 0, 0. Our model was like this. If we continue, in first iteration, the model from here jumped to there. You see, it's like the data was here, suddenly jump up there, and data is scaled down. So this is scaling down the data. It's the same data actually, because suddenly you see 0 to 30 jump to somewhere around 3000. So because of that, the data plot is scaled down. So in first iteration, because the learning rate was too big, model jumped suddenly up. Now, if we continue more, in next iteration, from up, suddenly jump down too much again, minus 300,000. So if you continue more, again, jump up. So, and if you run it yourself, the model is jumping like this, sees that the error is this side and wants to go toward, bring the model, and but comes too big, jumps overshoots the other side. Then looks at the data, oh, it was upside, then comes very much big side. So you should find good step that comes slowly and finds the proper point for training. So we answered that what is the good learning rate. For example, I show you here the good learning rate for this example is that if you continue, your model will try to find it. I will show you the implementation code quickly now for the same example. So linear one, I try to directly just run it. Okay, so if you look at the data visualization, what is happening? Each iteration, model comes and converges. I just plot two. Red one is previous, green one is new. I run it again. So it's still, you see that is iterating. So to make it more clear, everybody look at the slides, look at the screen. You can see that from 0, each iteration, our model, the green one is new, red one is previous one. Every time I show the previous one to show, you see this step. My model comes and converges. And here is still iteration is continuing, but the change is not too much. You see that mean square error is not reducing too much. And how this happened? Exactly what we did in the slides. Let's have a look at implementation. We did exactly what was in these slides. I just show it based on the examples that we have. We imported some libraries. I'm not repeating the explanations. And the data set that we explained already. So here I used only social media and sale. How much effect of social media on sale? I want to predict. This is input, this is output. So X is social media, Y is sale. I add the labels here. And here we have theta 0, theta 1, and theta 2 that in this one is not needed for now. We will use it in nonlinear model in next code. So what is our model? Our model is here. Y of the prediction is theta hat 0 added by theta hat 1 times X. So this is our model, linear regression model. So I show the calculation of residual sum of square mean square error, the same equation that we have. Number of iterations, I set 20 here, and learning rate that we want to adjust is something like this. So some stuff for plot, for plotting, creating plots here. I just ignore those. We come to main loop. We say for number of iterations, create a loop. How many iterations we want, create a loop, create a repeat. That we need to now calculate the gradients, what we discussed in the slides. So gradient of the theta hat 0 and gradient of the theta hat 1. So what was the gradient of theta hat 0? Was this term 1 over n times sum of the differences between two predictions. So for theta hat 1 is the same times x only. So if you want to double check it with these slides, I just want to show you here. This was the term that we calculated theta at 0, theta at 1 gradient, and this term we calculated in the slides. Exactly is implemented in our code here, these two lines. After calculating, we said that we want to update theta hat 0 by learning rate. Theta hat 0 is equal to theta hat 0 subtracted by learning rate times the derivatives of theta hat 0 and theta hat 1 respectively. So here I go to this slide. This slide's implementation is exactly over there with those two lines. Now here I predict again to show the new plot and calculate the mean square error. And like I calculate the RSS2 was not necessary here, then plot it. So these are all for plotting purposes. After I plot it, I iterate this situation until my error comes minimum. Here I didn't consider like amount of change. Here I just said number of iterations for simplicity. So if I run again, so what is happening in this for loop? For number of iterations, each time I calculate the theta. I need to again come out of this mode so that you can see. So in each iteration, we calculate the theta hat 0, theta hat 1, and update it by learning rate. If everything is fine, you will see that this is happening. So what if we change the learning rate? Let's try together. For example, let me say, okay, I add 2 more zeros here. Run it. So what is happening now? My convergence is low, is too small. So it's gonna take very long time that my model converges. It comes toward that direction of gradients very slowly. It's too slow. Even if 20 number of iterations is not enough to converge. So if your learning rate is small, then you should give more time to your model to train. So here is simple model we can easily see and quickly understand. But when we have more complex models, of course, will be we should be very careful with this learning rate and number of iterations. Second, what we do. So I just want to show you these two ones. So let's make it bigger. You see what's happening? The learning rate is too big now. Step size is too big. My model is jumping over up and down, tries to get close, but the step size is big and jumps over every time. and is not able to come to close. So any question? Is everything clear? Yeah? Line before. I just wrote two last steps. So this is like first is red, then I calculate new one, draw it with green. Then next step, this becomes red, green comes. So because of better visualization. Any other question? All right. So here we have a note about the learning rate challenge that we say proper learning rate, converge slowly enough, and find optimal solution like that. We have, as I told you, we have automatic approaches. One of the best approaches can be at the beginning. If you can set learning rate high, it means that at first, my algorithm can go with big steps, and gradually by time decreases the step size. That would be the best algorithm to work. Because if you are too big step size here, then you solve the problem. If too small, takes too long. So we can say at the beginning is like run or go fast, but later go slowly to find the proper peak point. This is very pretty common to be used, and it can help a lot for learning. In that implementation, I didn't do. You can try it yourself to see if it's good working or not. If you do that properly in maybe 1, 2, 3 iterations, you might, for that problem is simple, quickly converge. This is considered one of the best solutions. Now the question is, what is, we have nonlinear model. Instead of linear model, we have nonlinear model. It means that I have one more degree here. And how we were working with that, we said that we can add theta hat 2 times x squared. This makes the model nonlinear, and it gives you curve. Instead of this line, you will have like one curve. If you add more theta hat 3 to the x power of 3 and continue that, your model will be more complex. Like you will have more curves. Depends on the degree that you have. You degree add more, this model can be more flexible. And I show you one plot with 11 degrees in previous chapters. Now, what if is like that? What we should do with gradient descent? We say all the steps are same. All 5 steps that we studied are same. Just the step of the cost function is different. Why? Because we have other models. And when we changed our model, as I showed you there, the model looks like this. Y hat is equal to theta hat 0 divided by theta hat 1 x1, theta hat 2 x1 squared. So this is new. So when this is new, what we should do, we just need to calculate the gradient separately. But now we have 3 variables, 1, 2, 3. We should do it 3 times. What we do, we calculate the partial derivatives of the cost function 3 times. First one, exactly the same. Second one will look like this. We calculate. And third one, that is new, will look like this. Here at the end, we have x I1 to the power of 2. So, calculating the partial derivatives. Now, what about the update of the coefficients or update of the thetas? When I say coefficients, you know that we mean the theta hat 1, theta hat 0, and all those coefficients. So we do the same thing. Theta hat 0 equal to theta hat 0 subtracted by learning rate, partial derivative. This partial derivative is this equation. Same thing here, same thing here. Any question? Okay. Now I will show you that code too. The implementation for simple implementation for a quadratic one, or that slide is here. So we have the same concept, exactly same implementations, except we have theta 2. Here you see that I didn't initialize them as 0. I initialized them with something else, random number. Or you can write a random function too here, but in range of not too big values, like 0 to 1, or minus to 1 to 1. So we have one more parameter that in via prediction, you see that my model now is nonlinear. It has theta theta 2 times x to the power 2, as I've written in this on the whiteboard. And if I come down here, so I set some learning rate that is very small. And if I come down here, you will see this equal to slides. Now I have one more line that says, okay, the error calculation of the third variable. So for theta hat 0, theta hat 1, and theta hat 2, I need to calculate the gradient and update it. And because we need something there to theta hat 3 too. So this line 48 does that for me. And the same thing for updating the learning rate. And if I run it, I think I didn't adjust the values here completely, but let's see. We should stop this first and run new one. You see that my model is not linear anymore, and is like it has curve because I add more. And you see that it converts, and it stops somewhere around there. So we might try different values. Our model can maybe try to minimize better. Maybe seems like if the model, the prediction line is like this, maybe the error is lower. But we can compare it with the mean square, with the linear regression. This is nonlinear, or we can add dimensionality, add more parameters, add more non-linearity to see maybe my curve can cover it more. Like you can increase the number of dimensions to see that if you achieve lower error of the prediction model. Any question? I wish, yeah. Louder. Why become linear? I have no idea. It changed the curve and thinks that this is less error. The parameter for the parameter theta has to find something like 0. We let gradient descent to find us, right? That gradient descent after some adjustment converge to 0 and kind of don't use it. So with different parameters, with different changing, for other data set, might find better one. It's not based on us. It's based on the learning rate implementation, and tries different value and sees that for that one gets to 0. But seems like to me, I didn't adjust it, just randomly put some value. You can work on it to see if you can improve it. Learning rate, the parameters that we have. Over there, also initialization is important. I initialize this with some random number, like 0.1. So you should try different numbers, different values. But with adding the number of dimensionality, I think maybe you can also see that how gradient descent updates the curveness and if we achieve less error or that. Yeah, seems like, for example, this one is a nice example. Seems like it's stacking in local minima. All right. So We can have a short break, like 5 minutes, then come back. We continue with the stochastical gradient descent and mini batches. All right, let's continue the class. So now we saw the gradient descent, right? If we summarize it in form of algorithmic presentation, how it looks like this. If you want to summarize gradient descent algorithm, what we said, we first initialize weights, usually random. And your friend asked nice question. So if this is the mean square error line error, and our gradient descent finds the slopes to minimize it. Maybe we start in local minimum. So how to solve this problem? There are different approaches. One is like step size and learning rate should be good enough to find it. Second is you try multiple times with the different initial values, so that if you try different initial values, your model error starts from here, or maybe starts from here, or maybe starts from here, and you can find the best minimum and take that model that is best minimum. Something that maybe happens with second model. It starts from that initialization and ends up with that setting point too. Then, because I didn't do it by random, also I just put some values there for just understanding. That's just base understanding of implementation. So loop initialize, we loop until convergence. So initialize this, loop until convergence. Inside we compute the gradients. We saw how to do that. And update the weights. After updating the gradient, we update the weights. Theta hat, all the thetas. Theta hat subtracted by learning rate of this gradient. So that usually we call this like if we have I demonstrate as theta hat only, not 0, 1, 2. This is usually as a vector, that this vector includes all of them, that you should calculate it separately. So this is how we show the gradient descent algorithm. But there is a big problem, and what do you think it is with this algorithm? If somebody can guess. We have a challenge or problem. Any idea? No clue. Yeah. But local minimum? No. It is challenge, but the solution is that's problem of optimization, not gradient descent. Yeah. That's also a challenge, but we try different values to find out or use automatic way. And gradient values, if you mean the thetas gradient descent finds us for us. We need to only set the learning rate actually here. Any other idea? If you have a data set, our data set is with maybe 100 samples. If you have a data set with 1 million samples, now what you should do? The gradient descent should calculate the gradient for all of those 1 million samples. Partial derivatives of all 1 million samples in each iteration. And if that is image processing task, if it's image that we will see how to solve, then gradient of the all image, 1 million image per each iteration, that's unbelievably big. So how we solve that problem? So that's the problem that we have, computationally very expensive to for big data set to calculation of this one, because also is sigma sum of the all data per each iteration. That is tremendously big, and because of that we have, so in practice nobody use gradient descent. In practice we use a stochastical gradient descent, or is it actually better to say with mini batch third slide. But let's see first what's the stochastical gradient descent. So all the algorithm is the same. We say pick single data point of I for each iteration. So what does it mean? It means that if you have this model, instead of calculating all of them, if you calculate one, is also making sense, right? You will go somewhere close. You don't need to calculate all of them. But of course, this is nice. This reduced the load of complexity a lot, but would be sensitive, right? Then our data, if we have a noise, randomly choose the noise, and our model jumps toward noise much more, right? So because of that, the problem is that noise. Because of that noise, we also have another upgrade of this that we call it a stochastical gradient descent with mini batch. And mini batch says do the same thing exactly with gradient descent, but instead of choosing only one point, choose n data points each time. And this n data points is instead of one, say like from your data set 10, choose 10%, 5%, 2%, and then you have those samples. Then computationally less expensive and accuracy is too high. Instead of now, like your model will consider you want to update this model based on this only data, and line will be like this, like for one iteration. Next iteration you choose another one, then we'll adjust based on that. The benefit is smooth convergence, high accuracy for estimating gradient. We can increase the learning rate with this, and parallelized computation is also possible because when we are talking about the mini batch sizes, so this is also a very popular term in machine learning and deep learning neural network also, that we say, okay, if you choose these four for training your model, you choose another pack of four to train your model, so that you can parallelize this. Each one of these can be computed in different processors, different parallel computing units, then come to the end. So you splitting your algorithm training to identical process, so that this helps a lot for training process, especially nowadays in GPUs or a multi-thread or big servers. So mini batch selection in SGD updates the weight of using gradient computed for a small batch size, so that what we do, we usually shuffle the training data set, ensure is more uniform, is not like choosing one pack from one side that is bad. Then choose or divide the data set into mini batch sizes. It's pretty common to use 16, 32, 64, up to 520 sizes of the mini batch in order to train your model. So if you are working or you work with image classification or image processing learning algorithms that later on we will see, that we also will use the mini batch sizes, how many mini batch sizes we should use. We have limitation to the size, because when you use 512, for example, it means that 512 images for each model that I have will be trained at the same time. And usually your graphic cards have limited memory. So this usually should be optimized by the graphic cards memory that you have. You cannot make it bigger mini batch. So this should be based on your graphic cards memory, especially my students who working with deep reinforcement learning algorithms nowadays a lot. They are training deep learning models inside the reinforcement learning algorithms, and mini batch is very important because they make like 400 different environments for agent to train, and each agent has its model, its training model. So this size, if it's big, then number of samples that you load from dataset is too big, and that's hard to set it in your graphic card's memory. So that's also relation of the mini batch size with memory. This is very confusing for machine learning students. So that's come from here. Even if you Google, you study They're written, they make sense. You read and understand it a little bit, but quickly forget it. But now exactly you know where it is coming from. It is coming from gradient descent, statistical gradient descent, and the sizes that we have. What is the idea of having multiple batches? Iterate over the data multiple times can lead to have better results, first of all, then hardware and memory limitations can be managed. So as practice for you, you will run a statistical gradient descent, SGD, and give an example, then change it to quadratic and multivariate. So after we finish the class, after finish the slides, you will practice this one. Just it's simple change. I will give you the code, then you change it to quadratic and multivariate. So now, apart from understanding very important algorithm, gradient descent, SGD, and SGD mini-batch, we want to talk about validation. What is the validation? We already said that we have different metrics, right? Like mean square error, like F-score, like 6, 7 different metrics. Now, after training your model, can you only report the mean square error or those metrics that we have and say, I'm done? The answer is actually no. In order to prove and in order to show that your model works pretty fine, you should have some validation approaches. Validation approaches idea is like saying that you cannot just run your model and say my mean square error is this, or all the metrics that we studied, F statistics, p-value, all of these are this and done. And this is working very good. My accuracy is 98%. No. What you should do, you should show the validation result for your model to make sure that, yeah, your model is very accurate. And that's called cross-validation. So the definition, in the definition of cross-validation, we say it's a technique to assessing the performance of the machine learning models. Any model that you have, if a student comes to me and says, I have a model, I want to graduate my thesis, my master thesis with machine learning model. So my result is this. First question I ask, do you have the cross-validation result? Show me. So you should do the same thing also with whatever you're working on. So it is to evaluate how well a model generalized for unseen new data. And in cross-validation, we divide the data set into a number of smaller subsets, and we name these as folds. And then generally we train model and test multiple times with different folds. It's like if I show one approach that we will see in the slides quickly now, you have your data set. This is your whole data set, 0, for example, to 1,000 samples. You divide it. You train by this part, and you test. Right? So far, you know. You say, oh, we know already this. We want to do that, right? But with cross-validation techniques, what you should do, you should switch it. So if test was this, next time you train it with the other rest, the test is this. The other time, the test is this. The other time, the test is this, for example. Then you report the result. So we report the average performance of the model over iterations that I showed you there. Metrics are already the same, p-value, MSE, t-statistic, all the metrics that we discussed already are there, but are reporting by average of iteration on your data set, but switching the folds. There are different approaches. K-fold cross-validation is one of the most popular one that we will see. I also already explained it. We have the stratified K-fold cross-validation. We have the leave one out cross-validation, LOOCV. We have time series cross-validation and group k-fold cross-validation, and etc. These are the most popular one. If you read any research, if you see the machine learning model, most likely 99% you will see one of these terms that they say my validation was cross-validation or k-fold or LOOCV. So you will understand that how they evaluated their model performance, which technique they use. Techniques are simple. Let's have a look how they look like. So in k-fold cross-validation, it is most common approach that usually most of the research show this, and it is like pretty accurate. As I told you, divide the data set into k equally sized folds, and the train model with k minus 1 fold. Then test the model with remaining folds, and repeat this time by switching the test one. So exactly the same thing that I draw on these slides. At the end, you report the average of the performance for all the runs, not only one run. The mistakes that 90% of students, without knowing this doing, just they divide it and test it and say, okay, my algorithm works pretty good. That is not. Then in practice, we change the test from this one to this one, nothing works anymore. So, or in practice, they test out their model works, but bring it to real environment and test it with data. No, that doesn't work because they didn't do cross-validation and they are not sure that the parameters that they have found is well defined for all the tests, not only one test. That gives you stability of your algorithm. That gives you reliability of your algorithm in industry, in robotics, in prediction, whatever you are doing. Is not like sometimes working, sometimes not working. Most of you have this problem, right? You do something, sometimes it's working, sometimes it's not working. That technique is prevent that situation. So the main advantage can help fine-tune the model hyperparameters, can help select the best model from the different candidate models. Maybe you have different models, you can choose which one to use, can help to overcome the risk of the overfitting too. So because if you do this, you won't be overfit because you have to fine-tune to all of them, not only one test. Maybe you overfit for this data set, for this test data set. So how to choose K? You may ask how to choose K. How many folds should I divide? So the general answer is that there are experiments that the experiments, of course, depends on several factors, but the experiment says that first of all, consider your data set size, how big it is. A small data set, for small data sets, choose larger value of K. Computationally cost, increasing number of K, increase number of the times that you're trying. Also, that is important metric. And bias variance trade-off is the metric that we talked about it, how complex your model is. A smaller K may lead higher variance. That's also you should consider. Nature of data is also important. If the data has a specific structure, you may use a specialized cross-validation technique that we will see. Usually, but is pretty common to choose something between 5 or 10. So this is a general rule. Like generally, if you have normal data set, nothing specific, like split it into 5 up to 10. I usually do 7 for my experiments and data for cross-validation. Okay, any question? Right. So if we continue challenge of the k-fold cross-validation, we say in k-fold, we divide data into k equally sized folds without considering the distribution of the classes. Sometimes your data set has some distribution of classes, different class of data. Your data set is something specific. It's not that easy that is like we are putting some points and plotting over here. So that's one challenge that we might have in cross-validation if you have a specific data set. For example, also other sample is like if you have many samples of particular class, but others a few. Like you have one class of some data 1,000, some other 10 only. So that's a bit challenging. It imbalances the data set for your problem. In order to solve this, we have different other classes of algorithms. One is stratified k-fold cross-validation, that we say it's similar to k-fold cross-validation, but differs how to change the how to choose the sum from sample distributions. So what does it do? For each fold maintains the same proportion of the samples. Says, okay, if you have, let me draw it here. If your data is like this, like a lot of these red points, these are in one class of your data. You have second one is like this. Second data that you have in k-fold, it just says divided to k-fold. So when you divide it into k-fold, so for example, like you divide like this, then one of the folds has lots of these and one of the folds doesn't have, right? This is not good distribution of data. But in Stratified says that only, for example, you choose, if you have two class of data, change, like take 10% of this one, other color, green would be better. Take 10% of this one and take 10% of this one. If you have many, 10% of each class. So to make sure that your class choosing distribution for test set and validation set is proportional. Idea is simple, just says that make sure that you're choosing properly your data. And that's called stratified k-fold cross-validation. Third technique is leave one out cross-validation. Third technique is a specific case of the k-fold cross-validation, so that k equals to number of samples. We say, okay, each one of these equal to one sample. Like we classify these to k, very big numbers. Then what we do at each iteration, use a single data point for validation and remaining points for training. So, of course, it's clear that LOOCV is computationally expensive, because every time you are validating for each one. You train with all and validate with one, validate with one, validate with one, validate with one. One by one you do that. On the other hand, also has higher variance in performance, because you're validating each one by one. But why it is useful? Because it is useful in small data sets. If your number of data is small, k-fold cross-validation doesn't make sense much. Then you use it with small data sets. And also you can use it with stable models. That is, they are less sensitive for small changes in the training data. Okay. Third technique of the cross-validation that we study is the time series cross-validation. Sometimes your data is in time series, just can't keep coming. For example, trade market prediction, weather prediction, any prediction that is in time series. So, time series cross-validation designed for time series specifically, and in each iteration we train model up to certain point of time. So we have like time A to B. Then we train it based on that, and we repeat the window. Looks like this. The data in time series is coming. You choose a train and test time. Like you say, like if it's years, like 5 years of train, 1 year of test. 5 years of train, 1 year of test. you do like that. Then like you can predict the cost of like the trading or the value of the currencies or the value of the gold prediction, how much is gonna be expensive or lower. Then you can use this kind of cross-validation technique as time series. And next approach is group k-fold cross-validation. That is also one of the known ones that says when data sets contains groups of related samples, then split the data into k groups first, identify the group within the data set, for example, one hospital data that we have. Then exclude the validation set as each iteration exclude one of the groups of the data set and evaluate the model. And this idea says that, okay, in some data sets, is also useful, says, okay, consider whole group of the class to remove from data set to try that in that group it works pretty fine or not. And you, of course, iterate this. At the end, you do the total, return the total average. This is a case for a specific data set that for data set, you might need to try to see if, because your new data that is coming is whole class, like a scenario that is like complete new scenario, the data comes complete new scenario to your model. That new scenario is like something new, and you want to see if your model can distinguish this class completely, not like we haven't seen already samples of that. If it's possible to identify whole class as new data set, then you use the group k-fold cross validation. Okay, any question? All right. You will have assignment for next week. The assignment is for practicing you, to making you more familiar with what is happening with our implementation, continuation, and you develop your own practice at home. We say that use or extend the sample data set for our advertising problem, the code that I gave to you, and apply one of the proper cross-validation approaches and try a statistical gradient descent mini batch to fit the data. So you need to do two steps. I solve gradient descent for you. You change it to a statistical gradient descent with mini batch. So you determine batch size of, for example, 4, 3, 5, 6 for you and train the model that we have many times. After you did this, you apply cross-validation approach. Cross-validation, it means that the data that I gave you, you split it to, for example, k-fold. Then k-fold, or for example, you can use LOOCV algorithm as cross-validation technique. Then report the average error of your training process. It is very simple. Like you can do it in less than 50 minutes if you are a bit familiar. And what we studied today? Today we first discussed the gradient descent. Then we move toward the statistical gradient descent. Then we added the mini batch technique to that. Very important, very useful in machine learning. We will use it a lot. Then we introduce cross-validation approach, including many different techniques. For example, k-fold, stratified, LOOCV, time series, and group k-fold. And that was all for today. Any question? If you don't have any question, that's good. So we have about 1 hour. You open your computers over here. I will share you the slides, the code, and you first try to have a look at the code and change the hyperparameters to see how it's working. Then do the practice. We have one assignment, one practice. Practice is for class. Open the slides, do what practice says for you, try to change the code, and finish it today in 1 hour that we have. So, yeah, good.